In this tutorial, we will be discussing the common ion effect. So what is the common ion effect? It is an anion or cation that is common between the two chemical reactions. For example, HF and NaF both have the fluorine in common. A common ion can influence the environment of a chemical reaction by altering the pH or the solubility. Common ions play an important role in buffer solutions. Conjugate salts is a common ion of a weak acid or a base to make the buffer. So let's take a look at this one. We have acetic acid and sodium acetate. Separately, acetic acid has a pH of 2.9, while sodium acetate has a pH of 8.9. Once you combine them, they even out. So let's determine how to solve for the pH of one of these solutions. First of all, let's look at it as if it didn't have the common ion effect. So we have NH3 dissolving in water. Initially, for NH3, we have a molarity of 0.25. Water doesn't count because it's a liquid, not aqueous. And we don't have any of the ammonium or the hydroxide to begin with. So things are going to shift to the right. Which means it's 0.25 minus x, and x. Initial, change, equilibrium. So let's set that equal to our equilibrium constant. So x squared, x times x, over 0.25 minus x, the products over the reactants, is equal to 1.80 times 10 to the negative 5. We're going to assume that this x here goes away because the amount that's being disassociated or ionized is minimal. We're going to double check this at the end. So first thing we want to do is cross multiply. That gives us x squared is equal to 4.5 times 10 to the negative 6. We got to get rid of that squared, so we're going to take the square root of both sides, which gives us x is equal to 0.00212. Up here, we stated that we were going to wait and see if that x is really insignificant as far as in comparison to the 0.25. So let's double check that. So 0.00212 divided by 0.25 times 100, it comes out to be 0.84. Which is far less than 5%, so that means our assumption is okay and we can move on. We indicated that our x from the previous slide was 0.00212. Now you'll notice that gives us the OH because x is OH. So that means the OH concentration I can go ahead and take the log of this, but this will give me the POH, not the pH. So the POH is 2.67. And you may remember that the pH plus the POH needs to equal 14. Therefore, the pH is is going to be 14 minus the pOH, which is 2.67, which comes out to be 11.33. Keep that number in mind because we're going to compare this now as if we were adding a compound over here and making it a buffer solution and having the common ion effect. So let's take a look at if it is a common ion effect. The pH is 0.25, the exact same solution. But now we're including 0.1 molar of ammonium chloride, which chlorine doesn't do anything because it's the conjugate base of a strong acid, so it has no desire to absorb any hydrogens. However, ammonium, it does do something. That's our common ion. So we're going to go through the exact same process, but now instead of having 0.25 and zeros on the right-hand side, we're going to end up having 0.1 on the right-hand side. So let's take a look at this. I'm going to scribble that out so it doesn't confuse me. Alright, so NH3, we still have 0.25. H2O, I'm still not going to worry about because it's a liquid, not aqueous. Now we have NH4 being 0.1. And we still have OH, we're assuming to be negative, or assuming to be 0. So that's initially the change minus X, 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 and then equilibrium would be 0.25 minus X, 0.10 plus X, and X. We're going to set up the constant, we're going to set up this equilibrium to the equilibrium constant of an H3. So the products of the reactants, 0.10 plus X times X over the reactants of 0.25 minus X is all equal to the equilibrium constant of 1.8 times 10 to the negative 5. If you don't know where I got that number from, it was the equilibrium constant of NH3 from the previous question. Now, this minus X and plus X, I'm going to assume that the X is very small in comparison to the 0.25, and this X is very small in comparison to the 0.10. So I'm going to leave it out of the equation just to make my life easier. I'm going to double check this at the end. So that means we have 0.10 X over 0.25 all equal to 1.80 times 10 to the negative 5. Cross multiply, and I get 4.5 times 10 to the negative 6. And divide by 0.1 on both sides. So 4.5 times 10 to the negative 6 divided by 0.10 gives me 4.5 times 10 to the negative 5. I want to double check my assumption. Since I'm comparing it to 0.1 and 0.25, I'm going to go ahead and compare it to 0.1. So 4.50 times 10 to the negative 5 divided by 0.1 times 100 comes out to be 4.50 times 10 to the negative 4, which is plenty small enough. It's way smaller than 5%. Okay, so from here, this is my X. I can then figure out the pOH, because remember, this is giving me the OH, not the H. So pOH is negative log of 4.5 times 10 to the negative 5. That gives me pOH is equal to 4.35. So pH would then be equal to 14 minus 4.35, which is equal to 9.6, approximately. Now, look at this pH. Let's compare it to this one. Without that NH4 added, it was 11.33. It's very, very basic. Once we added the NH4, it's still considered basic, but it's less so. And that is the result of the common ion effect.